The land of mathematics is an exotic and puzzling place. A strange language is spoken there, with talk of homeomorphisms, differentiable manifolds, and transfinite numbers. But also to be found there are magnificent landscapes, spellbinding ideas, and occasionally, even useful things. So let's take a whirlwind tour of the land of math. You just need a guide, that's me, and a functioning brain, that's you. We're not really going to do any math, just take a look at the countryside. What could be more pleasant after a long hike through the jungle of numbers than a nice siesta in the shade? And what could be more pleasant for taking a siesta than this hammock, the profile of which looks uncannily like a parabola? A little reminder, if f is a function of the second degree, meaning that the highest power is 2, and if we represent x along the horizontal axis and f of x on the vertical axis, the resulting graph will be a parabola. Where the parabola cuts the horizontal axis, we find what are called the roots of f, meaning the solutions of the equation ax squared plus bx plus c equals 0. But for certain values of a, b, and c, the parabola raises up above the horizontal axis. In this case, it seems that there is no solution. And yet, any mathematician will tell you without any hesitation, a second-degree equation always has two solutions. But these solutions are sometimes complex. What does that mean exactly? It's impossible to take a siesta when a question is annoying you. So we're off for a picnic on the complex plane. To find a beginning to this story, we could try 16th century Italy. Far from the purity which it would later display, mathematics of the time mixed with astronomy, astrology, mechanics, and more or less everything. Girolamo Cardano was a typical mathematician of the time. He earned his living as a doctor, became famous as an astrologer, and invented the calculation of probabilities to win at cards. He published dozens of works on all sorts of subjects, from natural sciences to divination, via the interpretation of dreams, cryptography, and in 1545, algebra. In his treatise, modestly entitled Ars Magna, the Great Art, he revealed the grail of mathematicians of the time, the way of solving third-degree equations. For an equation written x cubed plus cx equals d, x equals this. A few of his colleagues had discovered the formula before him, but he was the first to publish it. It functions very well in certain cases, but in certain others it gives results which are strange. Take this equation, for example. The trained eye will quickly guess that 4 is a solution of it. But if we apply Cardano's formula, we get this. Is 4 equal to this complicated formula? Hard to say, but in any case, there's a problem, which is that the square root of minus 121 doesn't exist. In the 16th century, as in ancient Greece, a mathematical object wasn't taken seriously unless it could be associated to a geometric representation. A square, as its name indicates, suggests a surface area, and a surface area is always positive, to the point that the square of a negative number is also positive. There is no negative square, and therefore no square root of a negative number. Cardano filled equations of this type under the heading casus irreductibilis, irreducible cases. Basically, he abandoned them. Our picnic would appear to be coming to an end. Almost a century after Cardano, the mystery of the irreducible cases remained unsolved. And it was René Descartes who was to baptize these strange numbers, which are not numbers. Like many savants of the 17th century, he was as much a mathematician as he was a philosopher. And like all self-respecting mathematicians, he took an interest in algebraic functions. What's more, he was the one who invented the notation which we still use today, in which x and y are the unknowns and a, b, c, d, the parameters. By varying the parameters of a second-degree equation, we obtain all sorts of parabolas and all sorts of solutions. Descartes classified them in 3 categories. There are the true solutions, those which are positive and correspond to physical lengths. There are the false solutions, those which are negative. And for certain parameter values, there are the irreducible cases of Girolamo Cardano, where we find the square roots of negative numbers. These cases did not seem to correspond with any quantity. He called them imaginary solutions, and the existence he accorded them remained purely virtual. However, equations constantly led back to these imaginary entities, which can be written as multiples of the square root of -1. It was the Swiss mathematician Leonhard Euler who finally managed to solve and express their presence by using the notation I for imaginary equals the square root of -1, while not being able to clarify the mystery of their existence. But why? If these imaginary numbers clearly had no sense, why not just abandon them and move on? It's a question of closure. We say that a mathematical object is closed for a given operation when the said operation never takes you outside the set. When we add two natural numbers together, we obtain another natural number. When we subtract them, that is not always true, and hence the invention of negative numbers, which we regard with suspicion, but which we can't really do without. The problem is the same for roots. The square root of a real negative doesn't belong to the real set. So the real set is not closed for the operation roots. In a certain way, there's a leak, and plugging it requires imaginary numbers. Our story continues in Denmark. In 1796, the first precise map of the kingdom had just appeared, and the following year its author, a certain Caspar Wessel, at the age of 51, defended a thesis in mathematics. Published in Danish, it went more or less unnoticed in the rest of Europe. However, what Caspar Wessel had discovered was nothing less than the geometric signification of imaginary numbers. To understand his idea, let's return to the good old horizontal axis, which represents numbers as all vectors starting from 0. Multiplication by a negative number inverses the direction. But another way of representing this inversion would be to say that the segment goes through a rotation of 180 degrees. So when multiplied by itself, a negative number becomes positive. For a number I to become negative when multiplied by itself, it would need to be halfway through this 180-degree turn. Halfway meaning here. This strange number, which is neither 0, nor less than 0, no more than 0, becomes possible if we allow ourselves to imagine the domain of numbers extending into a second dimension, along an axis perpendicular to that of the habitual numbers. Numbers escape from the line and invade the plane. 30 years later, the great German mathematician Carl Friedrich Gauss baptized this new entity the complex plane. Here we are at last. The complex plane is here. Time to bring out the picnic and take a moment to see how this works. Complex numbers means that they're composed of two distinct parts, a real part and an imaginary part, which together define a point on the plane. To add two complex numbers, we place them end to end. To multiply them, we add the angles and multiply their lengths. Multiplying by I gives a 90-degree turn, so I, when squared, as expected, equals -1. Imaginary numbers invariably possess two square roots, and they never go outside the C-set, which is therefore closed to the extraction of roots. Now that we are familiar with the complex plane, let's return to our our graph, and try to visualize what's happening. The x-axis, which we took for a line, has become a plane which we were looking at from one angle. This becomes apparent as soon as we move up a bit. If we take the function which we had just now, the one which was useful for taking a siesta, and apply it to real numbers, it gives the parabola we saw before. But if we apply it to complex numbers, our graph spreads out into four-dimensional space. And what's demonstrated by this splendid multicolor hammock, the colors of which represent the missing dimensions, is that our function still has two solutions. For certain parameter values, these solutions are real, but for others, they break away from the line of reals and become imaginary or complex solutions. Our mathematician was therefore right. A second-degree equation always has two solutions. But there are sometimes imaginary or complex solutions. Imaginary, a decidedly ill-chosen name for objects which neither physics nor mathematics can do without. From Girolamo Cardano to Carl Friedrich Gauss, it took 3 centuries to arrive at this strange picnic. Not much, really, compared to the very long discussion which has been going on between mathematicians and mathematical objects for several millennia.